Welcome. It's wonderful to see you all, wonderful to have you with us today. And what an honor I have to introduce Professor Sanjeev Mukerjee to discuss with us this huge question of clean energy. You know, it's on everyone's mind. Every time I take a drive, I think, you know, how is this the shortest route? How much gas am I using? How much gas am I putting in every week into my car? Could it be less? There's a real, I think, awareness now that we have to be very strategic as a society, as individuals, about our energy usage so that we can really try to prevent climate change progressing any further, so we can be really better stewards of our planet Earth than we have been. Professor Sanjeev Mukerjee is one of the people who is really working on this, and it's a great honor that he's a member of the College of Science and of Northeastern University. Professor Mukerjee is professor in the Department of Chemistry and Chemical Biology, where he heads the Center for Renewable Energy Technology. He has more than 3 decades of research on what's called electrochemical material science, which means he's worked at the front lines of battery, fuel cell, and electrolyzer technologies. You see, he's going to have to explain that to us because even I can't pronounce that. He's a fellow of both the Electrochemical Society and the International Society of Electrochemistry. He is the recipient of the Klein Lecture, Excellence in Research and Creativity. He's a college distinguished professor, and he was also named Ford Research Professor. What a wonderful set of accolades, so deserving. The research that Professor Mukerjee focuses on lies on the fundamental aspects of charge transfer at an electrochemical interface. Again, I'm sure he'll explain to us what that means. His work involves synthetic chemistry and ion transport media in conjunction with spectroscopy, X-ray absorption, and scattering techniques. Most of his research is a hypothesis-driven fundamental effort designed to answer some of the most critical questions in material structure, and that lead towards understanding of how we can move towards better, sustainable, renewable energy sources. It's my great honor to welcome Professor Sanjeev Mukerjee to our discussion today. Thank you so much, Sanjeev.
Thank you very much, Hazel. I hope all of you can hear me. It's a wonderful day, wonderful spring day. So I really appreciate your taking this time to hear me. So I'll begin by start sharing my screen. All right, I'll put it on full view. I hope you can see the presenter mode, or actually my slides. Anybody?
Yes, great, Sanjeev.
All right, so let me start my talk with something which we all know very well, and that is our challenge with global warming. And you know, this thing, as you can see from all of these these figures I have up on the slide, talk very much as to our collective challenge. The title of my talk is Innovating to Zero. It's shamelessly stolen from a 2011 TED Talk given by Bill Gates. And as in his inimitable style, Bill Gates really translated down to this whole problem into an equation. And so you can see in the bottom left-hand side, his famous equation, which basically translates into, having this whole problem of our attempt to innovating to zero carbon into 4 possible factors. One is, of course, the number of people. Second is the service per person. Third is the energy per person, and the fourth is CO2 emitted per unit of energy. Now, if you look at all these 4 factors, the first 3 factors in any democratic society is absolute no-go, because you obviously can't tell people not to have children. And actually having more children is turning out to be a demographic dividend, not actually the other way around. Secondly, you cannot tell people to consume less. That is not going to happen unless if you want to remain in office. And the third thing is, of course, the energy per person or per service is obviously going to depend on the quality of life. And so you cannot also ask people to compromise on that. So the challenge, therefore, is on the factor C, which is lowering our carbon dioxide footprint per unit of energy. And that's what we are set out to do. We really think that it is possible, and hence really control the exponential increase in our global surface warming, which we see, which has really exceeded most of the models which organizations such as the IPCC, for example, had predicted. So right now we are exceeding 400 parts per million in terms of CO2 concentration. And that is actually translatable to the amount of global fossil CO2 emissions. And you can see all the global events outlined here where you have seen dips in the CO2 emission. The first one was the dissolution of the Soviet Union in the 90s, early 90s. Second was the global financial crisis, which saw a dip. And now we see an even bigger dip, actually, for the COVID-19 pandemic. But notwithstanding all these dips, our increase in the global CO2 emissions have been progressing higher. And, so essentially, if you can look at the bottom right-hand side figure, we have really exceeded the carbon cycle in terms of accumulating CO2 in the atmosphere. And as all the scientists tell us, the effect of this is going to be catastrophic. So what can we do about it? Well, we have done a lot about this. As you can see from my next view graph and the one after this, all the renewable sources of electrons, we all know solar, wind, geothermal, hydro, and nuclear, out of which geothermal and hydro are essentially geographically limited. But solar, wind, and nuclear can be put anywhere. As you will see from my next view graph, nuclear is, however, very, very expensive at the moment and needs a lot of work to bring the costs down and, of course, improve its safety record. But solar and wind have had an impressive record in terms of the price of renewable electrons. And I'll elaborate on that in the next view graph. But what we do here at Northeastern is take those renewable electrons and then translate that into society. And one of the best ways to do it, and actually the only principal way to do it, is using electrochemistry. And so our efforts have been basically divided into three thematic zones. One is transportation and distributed power. The other one is carbon neutral fuels. And the third one is energy conservation. So this basically are the three themes on which we work. Of course, they're all based on electrochemistry and, in a sense, the electrochemical interface. And in order to make it happen, we use every aspect of electrochemistry there is. That includes electrodeposition and dissolution, electrocatalysis in a very big way, redox chemistry, electrolyzers, and, as you see in your lithium-ion batteries, intercalation compounds. And that covers a whole range of technologies ranging from energy conversion to energy storage to electrolyzers to electrochemical pumps and energy conservation. So I'll elaborate on all of this, but at the heart of all of this is the cost of renewable electrons. And as you can see right now at the 2020 level, the cost of renewable electrons in comparison with even the non-renewable forms such as coal and gas combined cycle is the lowest. I mean, this is the lowest cost of any kind of energy you can at the moment. And so this is really a wonderful opportunity to try and make the best we can out of this boon we've had out of technology development over the last 20, 25 years. And the biggest drop in that cost of installed renewable electron is in the solar photovoltaics. That is really an amazing development which happened in the last 10 years, which has brought this really into the forefront of our usable energy sources. And you can see that right now the Wind and solar projection is increasing, as you can see from the top right-hand plot. And you can see the coal is dropping really dramatically. And some of this gas increases because it's replacing coal very rapidly as the principal source of current state-of-the-art source of energy. Nuclear, in terms of its installed capacity, has remained constant, and that's always been a rather unfortunate thing, because whenever nuclear starts to get its due attention, some catastrophic event happens which brings it down politically to a no-go. Last one being the Fukushima incidents. The hydro has its own political issues, but I think hydro is one of the very attractive means, and there is still enough opportunities to exploit hydro to make a baseline power source happen. So with that, let me first talk about what we are doing at Northeastern, and that involves transportation and distributed power. We all understand transportation. We've seen our rapid transformation from gasoline-powered internal combustion engines to battery-powered vehicles. That's happening really rapidly. Every single car manufacturer has got plans to do this kind of transition. The distributed power is the other thing which we haven't heard of enough, but is also very important. Right now, what we have in the United States is a 1950s designed distribution of electricity across the country through centralized power generation and utilities which distribute this power across the length and breadth of our country. But we've seen that with advent of more and more catastrophic storms, we do have outages which are not in days, but are in weeks. I remember the Sandia storm, which happened almost 10 years ago, which pretty much put parts of New Jersey and New York out of power, and even Connecticut out of power for not days, but even better part of a month. That is unheard of. And for those, we have to be resilient. And one of the ways to be resilient is to use combined heat and power systems, which are community level power generation units. And these can be achieved through fuel cells. And we are working very hard to actually enable that. And for this, the fuel cell has to have a heat point, which is, in terms of temperature, around 150 to 250 degrees Celsius. That's the best usable heat in terms of exergy. And so that's what we are working on with companies such as Advent Technology Holdings, and to bring it into reality. Now, in all of these attempts to bring fuel cells, and of course, one thing I'd like to mention before I move on is transitioning from batteries to the next generation of electric vehicles will be fuel cells. And the fuel which will power this, and I'll talk about it in more detail, is going to be hydrogen. So hydrogen is the next fuel of the future. We have to build the hydrogen infrastructure across the country. There are ways to do it, and I'll elaborate on that, but that is the way of the future. Batteries can only take us so far in electrification, but ultimate electrification will happen with fuel cells. But the big problem with fuel cells is right now we need noble metals to make it happen. Now, there are problems with noble metals. Most of it comes from South Africa. Now, that's not a problem, but it is in terms of dependency. And it is very important that, therefore, we lower our requirement on this one strategic metal. And you can see that the cost of these metals is also very important. As you increase the number of fuel cells produced per year, which is very modest here, which is only 500,000. If you exceed 500,000, then almost 50% of the cost of the fuel cell is just noble metals. Now, we've worked for better part of 2 decades to try and bring the loading of these noble metals in fuel cells down. And actually, the current Department of Energy idea of enabling this is to replace the catalytic converters, which generally contain 5 to 10 grams of platinum, to actually have that same amount of platinum into a fuel cell, because once you have a fuel cell powered car, you don't need a catalytic converter. because your tailpipe will only have water vapor coming out. So you can see that as a strategic material, this fuel cell costs, the noble metal costs do see fluctuations. This is platinum fluctuation, happened in January 2008 because of the economic crash. But in general, the platinum cost has been going up and down quite vigorously. It generally hovers around $1,200 a troy ounce, but can be as high as $5,000. Other materials which are part of the platinum family, such as rhodium, for example, has an even higher variation. For example, it used to be $6,000 a troy ounce about 6-7 years ago. Right now, if you want to buy it, it is $28,000 a troy ounce. So these noble materials are, in my opinion, unsustainable, and you have to go towards more sustainable materials. So designing these catalysts is a very important aspect, and we've been at the forefront of this for better half of 2 decades and more. And so this is what we have paid a lot of attention in our research group. And so one of those things which we were very fortunate was to get a Department of Energy grant about 10 years ago, which allowed us to really be at the forefront of the drive towards more sustainable catalysts. I won't go into details of all of this stuff on the view graph, but suffice it to say, we've been very successful at making what are called coordinated single atom catalysts, which are iron, nitrogen, carbon based systems. This was a team effort with us in the lead, but we also had many universities and a startup company which we helped form to scale up these catalysts. The startup company is still there and is the only company in the United States which makes fuel cell catalysts right now. Every other company is a foreign company, most of them European or Japanese. So just to bring one of these things which is unique to us is this fuel cell performance. You can see current potential curves. This is the common way to exhibit a fuel cell performance, and you can see what we have achieved with this. This is a fuel cell operating at 200 degrees, which is the fuel cell for combined heat and power. It uses a unique membrane, which is patented by one of the companies which we work with very closely, Advent Technology Holdings. And you can see that this fuel cell does not have any platinum at the cathode and shows remarkable resilience in terms of the durability as well as performance. We've been trying to develop this further into a product, and in the next couple of years, we're hoping we'd have a tangible product to demonstrate this technology with. The original sponsor, as I mentioned previously, was Department of Energy with their unit or subunit called Energy Efficiency and Renewable Energy Division. The other thing which we do is energy storage, and in there we are working across the board into all the aspects of energy storage you can imagine. The thing we are working with in terms of conventional lithium-ion batteries is to transition from the current state-of-the-art solvent-based electrolytes. These solvent-based electrolytes, as I will elaborate later, are prone to catching fire. And we have all seen, those who are interested in these batteries, that sometimes they can have catastrophic failure and lead to fires. And of course, that's not a very nice thing to happen, especially if you have these batteries flying in airplanes. And that's why there is always this safety question that do you have any batteries in your check-in luggage? That the reason for asking that question is because of this. If you have badly made lithium-ion batteries containing solvents, well, they can catch fire. So in order to mitigate that possibility, there are solid-state electrolytes, which we have recently been given a grant from NSF under the Industry University Cooperative Research Collaborative. And in that, Northeastern has 3 partners, but overall we have 25 industrial partners across several universities which are participating in this effort. And we hope to have commercializable solid-state electrolytes coming out of this endeavor. We have also, of course, this is the conventional lithium-ion technology, but we have to look beyond. So the conventional lithium-ion technology can promise you about 300-mile range if you power this, if you use these types of batteries in your car. But we want batteries which will last a week, a month, and so on. So for that, we've been working on the advanced or beyond lithium technologies. These are essentially lithium air and lithium sulfur. Lithium air, we've had a 10-year record of having worked on it. It's an extremely difficult concept. We haven't succeeded yet. It'll take much longer. In the meantime, we're working on lithium sulfur, and that actually has a promise of at least doubling the energy density of the current lithium-ion technology. But with these two, the costs are still a limiting factor. And in order to make large-scale energy storage happen, which are in the megawatt level, there are other technologies such as the ones involving hydrogen bromine. I'll have a few slides on that. You can see what that entails and how that compares with the other competing technologies. And also the ultimate one, which will be basically redox flow batteries, which we are working with Los Alamos National Laboratory and is funded by Department of Energy Office of Electricity. So let me talk a little bit about the hydrogen bromine system. You can see hydrogen bromine system compares quite reasonably with other similar redox flow batteries, such as the vanadium redox flow battery. And we are working both on the acid and the alkaline form. Right now, the project which we just completed for ARPA-E was in the acidic pH domain, but we are working on the basic pH as well, now that we have some wonderful membranes in that domain. But if you compare it with other technologies such as lithium-ion, fuel cell, or even gasoline, this storage technology is not as great as you would have in the other forms. But the big thing here is that the redox flow systems or hydrogen bromine systems allow us to separate the power density from energy density. So the energy density could be vast because you're basically storing a more reactive fuel to power your conversion cell to produce the power back. So it is actually still a very attractive form to save or store large amounts of energy. Now, this is particularly important when you consider a solar farm or a wind farm, because both of those are intermittent and you need a ballast to actually level out the electricity for consumption. So the main thing we have done in this hydrogen bromine side is work on the catalysts. And one of the biggest Achilles heel of these catalysts was that if you had a little pinhole in the membrane and the bromide ions from the anode side crossed over into the cathode side, you would have a catastrophic failure of the cell. And you can see that from the black line, the entire maximum power generation would just tank. You can imagine a megawatt level system where you have a catastrophic failure like this, that would mean millions and millions of dollars of loss. What we have been able to do is develop a catalyst which allows us almost 350-hour protection from catastrophic failure. This is enough time to change pumps and control the situation. So that is the big development which we did under this grant, and we have a patent for this, and we're talking to many companies to try and commercialize this technology. Moving on to the new stuff, that is solid-state electrolytes. There are many solid-state electrolytes right now, which are, various companies are trying to develop for lithium-ion batteries. We are working with them, as I mentioned before. And our job is to work at the fundamental aspects of how lithium transport happens in these systems, especially how lithium-ion transport happens at the interface between the electrolyte and the electrode. And that is what we are really known for, because as I will show you later, we do synchrotron spectroscopy, and that is at one of those really, really insightful ways to understand what's going on in the system. So as I think I briefly mentioned, the main reason for going to solid state electrolytes from the organic solvent-based systems is first performance and safety. So we can go from 690 watt hours per kilogram. I mean, right now, the traditional lithium-ion batteries are about 350 watt hours per kilogram and about 500 watt hours per liter. We can go to 690 watt hours per kilogram or 900 watt hours per liter. That's really an amazing increase in performance. And the most important thing is, of course, enhancing the safety, because there is no organic solvent to catch fire in these systems. And that would mean that we could actually have deep discharge cycles in these systems and improve the lifetime to about 10 years. Right now, the conventional lithium-ion battery, you can only discharge it to about 50% of its overall charge. You shouldn't go beyond that, because that severely limits its lifetime. In these systems, our attempt will be to do deeper discharge so that battery can actually take you longer distances and ensure a 10-year lifetime. Obviously, the other attempt, because of the safety aspects and the way these batteries are put together, we hope that the cost would also be much lower. At the moment, we have progressed from about $500 per kilowatt hour cost to close to 150, if you actually trust what Elon Musk is saying. But I don't see any reason why these costs can't be below $100 a kilowatt hour. So that's the other big thing. With the safety and performance aspect is the charge time, which is the biggest issue with these battery-powered vehicles. We hope that we can do much faster charge. I do not see, what is here in the view graph, 2 to 15 minutes. That's rather ambitious, but 30 minutes would be pretty close to what is achievable for a 75 kilowatt hour battery. So that is certainly something which is achievable. And of course, all of this will also be tied to the cycle life of the battery itself. So a word about lithium ion technology beyond the lithium ion batteries which we have right now. One of those is lithium oxygen. The attractive aspect of lithium oxygen is you don't have to carry the you don't have to carry one of the electrodes, because it is basically oxygen which is from air. So that's the attractive aspect. The other one, of course, is very high energy density. You can see from the top right-hand side figure, compared to the conventional battery technologies such as lead acid, which is in your automobiles, going on to the lithium ion and lithium sulfur, zinc air, lithium air. This is lithium air technology is as close to gasoline as you can get in an electrochemical system. So we worked for 10 years on this, and we hope we can continue to do this, because the promise is so much higher. But besides this, as you can see from this plot, we do have lithium sulfur, which is much better than lithium ion. And so we have just embarked on a new project from the Vehicle Technology Office and Giner Incorporated, which is here in the Boston area, to actually improve the cycle life of lithium sulfur. And for that, we are actually using a combination of both advanced catalysis as well as additives to the electrolyte. These are fluorinated additives, which we hope to bring about and also enhance our fundamental understanding of how these systems actually work. The other thing we are working very fervently, and that's one of the mainstay of our efforts right now, is hydrogen generation through electrolysis, and of course, hydrogen pumps to actually purify the hydrogen. So you can have impure hydrogen on one side and 3/9 pure hydrogen on the other side. We have done a remarkable advancement in both of these. Let me elaborate a little bit. So when you talk of electrolyzer, the electrolyzers, as far as the low temperature electrolyzers go, electrolyzers are not new. They're almost 100 years old. Started with the Norwegians and the Swedes utilizing their vast amounts of hydroelectricity they had to make hydrogen and advanced metallurgy, which that allowed them to do. But then since that, the main problem with with that liquid alkaline technology was that it couldn't go to high current densities and it was expensive. And since then it has transformed to acid membrane electrolyzer. But the acid membrane electrolyzer requires noble metal in vast amounts. And so it has been a niche technology to date. And what we are working on is alkaline membrane electrolyzers, which do not require any noble metals and hence bring down the costs and make it more viable in terms of the number of units you can make with it. So what we envisage is hydrogen produced at below $2 a kilogram, going to $1 a kilogram in every gas station in the country, utilizing renewable electrons to do so. So that's the dream. The histograms, as you can see, the green part is the cost of renewable electrons, which has obviously fallen. That is the biggest change and the game changer in this whole technology cycle. The other one is the blue part, which is the cost of the electrolyzer itself, and that has fallen because of because we don't require noble metals at all. So here we are. This is our progression for the last 5 years. From the red curve to the purple curve is where we have what we have achieved. And right now we are well below 2 volts at 1 amp per centimeter squared. I'll show you in the next view graph. We can actually achieve 3 amps per centimeter squared, not in a sustainable way, but at least in terms of for spikes, for meeting urgent demand and things like that. If you compare this, the noble metals, which is the dashed black line, those are we are doing much better than that. So we are well on the way to using completely noble metal free alkaline electrolyzers, where the hydrogen is produced almost dry at 3/9 pure level. This is the one which we recently have below 2 volts at 3 amps per centimeter squared. And it's remarkable that we can actually do that. We are world leaders in this performance. And right now we are in a hurry to patent as many patents as we can file in this area, as well as publications. The last thing I will mention is energy conservation. One of the things which I'd like to highlight is chlorine production. It doesn't sound terribly exciting, but chlorine actually takes up almost 2% of any developed country's electric output, including United States, which in 2017 numbers was 87,600 gigawatt hours per year. That's a lot of electricity. And there are 2 primary technologies involved here: chlor-alkali systems and hydrochloric acid electrolyzers or recovery systems. Hydrochloric acid is a particular point in case because the hydrochloric acid here is produced in a lot of chemical plants. These hydrochloric acid which are emitted from these plants are actually dilute hydrochloric acid with a lot of organics mixed in it. Nobody wants that. It's very expensive to get rid of. So the technology which we are talking about is what is called oxygen depolarized cathode technology, where what we have done is we have replaced the hydrogen evolution electrode with an oxygen reduction electrode. Both of them are reduction. And actually by doing that, we can save 1 volt out of a 1.36 volt process, which amounts to about 700 kilowatts of energy per ton of chlorine. That's a lot of energy savings. That's what we've been able to achieve. The current state of the art, especially in terms of hydrochloric acid technology, is rhodium sulfide. And in the beginning of my talk, I mentioned it's $28,000 per troy ounce. And that's why we have patented. There are 2 US patents which we just got a few years ago, which show that we don't need rhodium, and we are able to do the same, actually better, 20 to 40% better in terms of energy using our iron, nitrogen, carbon catalysts. It's amazing that these catalysts are stable, because in the hydrochloric acid case, we are using 5 molar hydrochloric acid. So that's an amazing aspect. So right now we are working with Denora North America to actually, prove that this technology works. And if it does, it's going to be a commercial product in the future. The last thing I'll mention here is our, in all of the effort in materials development, which I showed you as I moved along, is our ability to do advanced spectroscopy and computation. And you can see we use a vast variety of spectroscopic tools, and some of which are more mundane, such as the electrochemistry tools, but some of which are amazing tools available through the Department of Energy user facilities, such as the synchrotron light source. Here is an example. This is the advanced photon source, which we have been using for doing really the transient spectroscopy. We also do steady state spectroscopy, all in situ, while we are changing currents and potential in our cell. An example of such is shown here. These are very, very high power X-ray sources. So these are actually inside lead lined chambers. And some of the pictures are shown here just to show you how these are actually conducted. And some of our cells which we use for doing spectroscopy is also shown here. In our effort to actually advance all of this, we work very closely with national labs. We have very close relationships with Los Alamos Brookhaven National Lab, where we are using the synchrotron light source, National Renewable Energy Lab, where we work very closely in terms of the translational aspects of our technology, and Argonne National Lab, where advanced photon source exists. We also have many universities which we have been working with, a lot more than what I have in this view graph. These are our closest partners in the efforts which I just outlined. We also have worked with a lot of companies. We continue these efforts. We just finished a program with Ford. We worked with General Motors and so on. Too many to actually mention here. But I will show you some of the successes we have in terms of startup companies. This is also a global effort. If you look at all our publications in the last 10 years, they've been actually publications with collaborations across the globe. Some of these institutions are mentioned here. What I don't have here is our close collaboration with Israel. I am on the board of INREP, which is the Israel National Renewable Energy Program. Of course, we haven't met in the last 2 years because of COVID, but I really look forward to the efforts happening there. But since it was getting too crowded, I somehow didn't mention that. We have a vast portfolio of patents. I can elaborate on that in the question hour session if the question arises, both in the platinum group metal free area as well as the platinum group metal based systems. There are many startup companies which we helped found. I'm not the founder, I have to say that right at the outset, but I helped in a very big way to help bring them about. One of them is Protonics, which makes fuel cells for the military. It's now owned by Ballard Power Systems. Another one which was not successful was to make microfuel cells. I was most excited about this, but there were no takers for this. And so amazingly enough, it ended up in another startup company called AirRing, which is trying to develop some of the technologies which we developed for the microfuel cells for the CPAP disposable systems. We do have catalyst companies like Pajarito, where I'm one of the, not the founding member, but one of the members of the advisory board, and actually they were the first customers of my program. And the last one is Advent Technology Holdings. This is the company which is trying to develop fuel cells for trucks, combined heat and power systems, as well as the hydrogen electrolyzers. And with that, I will finish my talk, and hopefully there are questions.
Sanjeev, Professor Mukerjee, thank you so much. That was really fascinating, and what wonderful accomplishments you've made. Congratulations for everything that you're doing. It's really an honor to have you as part of the College of Science and Northeastern University. Maybe you could stop screen sharing and then we could see each other a little bit more. There we go. Wonderful. Let's take some questions, and please feel free to ask your question. As you know, there are only good questions. Every question is a good question. So don't be shy and think that you're not quite understanding things, because it was very complicated and technical, and absolutely there's a lot for us to all work on in terms of the understanding. Let me start with a couple of the questions that are in the chat already, Sanjeev. I'll read them. With a world somewhere predicted to be 8 years of the climate clock's point of no return to prevent unchecked global temperature release, what is the biggest impediment to scaling existing technologies or finding viable, sustainable energy alternatives? Is it economics, politics, government, or cultural cooperation?
I would say the most important, if you want something to be adopted by the masses, it has to make economic sense. And the thing is, for a long time, we've had rather cheap gas, and people, and you can see that the automobile manufacturers actually started moving away from making sedans and even, I would say, fuel efficient vehicles to SUVs. I mean, if you look at all the three US manufacturers, they are making more SUVs and trucks than they make fuel efficient sedans. And that was because of the rather cheap price of energy or gasoline. That's all changing with the war in Ukraine, and it's going to actually escalate, in my opinion, at least for the near future. So I think these battery vehicles will become more and more popular. They do have a very big issue, and that is those people who also want to use the same vehicle for driving long distances will have this issue about, need to recharge the battery. And so the battery infrastructure has to keep pace. It is actually happening, not only in the United States, it's happening in a country which I love a lot, which is India, which has a huge potential to making these things happen globally because of the scale at which it can be adopted. So I see all the right noises being made by India, for example. China has already put it in place. And so it is going to happen. It's an inevitable transition. However, is it going to happen fast enough? For that, a lot of things has to come to place. And that is, our politics has to work. Our, the population has to be made aware. So awareness has to be there. And also rapid escalation of research in this domain. If you look at the amount of money United States has spent in the last 10 years, we would pale into insignificance compared to Europe and China. They have spent 10 times more. And I think we still are the leaders. I mean, amazingly enough, we are still the leaders. People still copy and paste Department of Energy documents. Our papers are still read worldwide. But how long that's going to be, I don't know. So we really need to come back and really reinvigorate our research in this area. And of course, adoption of all of this into actual technology.
Thank you. Let me go to another question. These are all sort of related to one another, because I think the theme so much is what can be done with alternate technologies to do something to energy consumption, energy types that are available in what kind of time frame. And so, there's such interest in renewable energy, and the deliverables seem to fall short of the interest. For example, electric cars, I understand, have many limitations to where the fuel comes from and various aspects as well. But they can't be used in rural areas of many states because there's no charging network. If you want to drive from one end to the other of Vermont, one of our neighboring states, in an electric car, you're going to have a big problem because you really can't charge your car along the way. Do you think that the technologies that you're developing will help to address this in different ways? What's the sort of best possible scenario here?
Yes, there are two technologies which we are working can really be the game changer. One is the combined heat and power, that's decentralized power, because if you go to the rural areas, obviously there won't be that many people right now who have electric cars or trucks. It's already happened, however. If you look at Ford, they're making this wonderful truck called Lightning, which is absolutely fantastic. I mean, for contractors and people who work, out in the field, you don't need to carry any generators. It has a 440 volt outlet. It has a 120 volt outlet. So all those power tools one carries with, in a typical contractor's truck, those things typically require a generator there. You don't need it. Now, as far as recharging those batteries, that's the key. If you have community level power generation, then you take away one of these infrastructure issues which always crop up. So that's one. But the ultimate transition will be hydrogen. We have gas stations across the country, even in rural areas. You can just imagine that gas station could be a place for an electrolyzer producing hydrogen. Now, how fast that can happen will need some kind of policies by the government to help the economies of scale to happen. And that's what we are talking about. But just to let you know, if you look at the transition this country made from horse-drawn buggies to actual internal combustion-based cars, it was Standard Oil getting in cahoots with Ford and other automotive manufacturers and saying, wouldn't it be a great idea to have gas stations? It was a bigger infrastructure push than what we face right now. We already have gas stations. So I think that can happen really, really fast. Few things have to come together, but the main thing is society and politics, which as technologists, we don't pay that much attention, but I have a renewed respect for those who work in, as political scientists and in policy.
That's a very, very interesting. I think about the cars getting smaller, and there's a comment about, demand and and gas prices and cars getting smaller. But I also look at the United States, and there are lots of places where a four-wheel drive actually is needed. You go on muddy roads somewhere, or snowy roads, you really need a four-wheel drive. So whatever we do, even if the cars become smaller so that they can use less fuel and so on, there's kind of the reality of what the country is and what people in the United States really love to do and feel free to do.
So I can actually tell you that these electric cars are the ultimate four-wheel drives. Because in a traditional four-wheel drive, you have the front two wheels and then you have an axle which powers the rear two wheels, sometimes on demand, sometimes it's symmetric all the time. But these electric cars will mean that each wheel will have an electric motor. That's the ultimate four-wheel drive vehicle, which you cannot imagine with a traditional internal combustion engine with a transmission system. So that's what we need. Of course, a lot of things have to happen. The cost of electric motors have to go down. That's another story by itself, because electric motors require these rare earths, which are not exactly cheap at the moment.
Well, that is encouraging, I must say. There's a question also, which I think for us in universities is really important, which is the question of how do universities and research in universities contribute to really changing the landscape? I think about the research we do in universities as being at the frontier, that the job that we do in a university is to be innovative, to be creative, to push the frontier, to crack open where we're going. And that cracking open to unexpected findings, to new directions, is what can then interface well with industry to actually get products made. Do you think that that's true? That type of notion is true for this industry shift to better fuel sources? Do you think there's another model that we should be thinking about with regard to university contributions to changing our energy sources to something more sustainable?
Well, universities, most people don't recognize, but universities play an enormous role in transforming technology. You can see that the role MIT has played, for example, in the Boston area. I mean, it has remarkably changed the Massachusetts economy in a big way. I mean, other universities have played a role as well, but I'm just taking one case in point because it's one of the early demonstrators of how universities can create wealth and through technology. Not many people recognize, for example, that MIT and Massachusetts was the original Silicon Valley. All the mainframe computers were designed here, were built here. And we were at one time the source of computer technology. Of course, all of that moved to California for a variety of reasons. We are right now the biotech hub. There's no reason why we can't be the hub for innovative technology in renewable energy as well. And there are many companies here which not many people hear about. So where am I going with this? Universities play a huge role in bringing disruptive technology to the forefront. University's role is not optimization. I don't like the word optimization because that's the role of companies. University's job is to bring disruptive technologies, risky technologies, which we bring to the table through patents. We attract commercial partners to see if it will work. And if it works, they are disruptive. They completely upend the current state of the art. And that's why so many of the biotech firms are here. If you look at Moderna, I mean, when it started, nobody knew it would succeed. It was just an idea. And look at it now. I mean, that's the kind of transformation we are talking about.
So interesting. Let me ask one last question amongst this very interesting set that your audience has asked. We at Northeastern are really interested in building entrepreneurial students, in having our trainees be people who feel unconstrained to be creative, to be crazy, to think of things that really no one has thought of before and move them forward. How do you think, and you, I want to thank you, are helping in the College of Science to help build that culture of entrepreneurship. Do you see any particular ways that we should be more creative ourselves in allowing our students to become more entrepreneurial in this particular area?
Yeah, I think entrepreneurship comes from a environment which actually allows it to flourish. It cannot be as a one-off, or it cannot be taught in classrooms alone. Of course, the mechanics of it can be taught in a classroom, but then there has to be a cohort of students who actually don't want to go out looking for a job, but want to take their skills and their knowledge and go out and start a company. You can see that happening in many, many places. MIT does that. If you are a graduate from Stanford, most of them are not looking for jobs, but they are talking to venture capital people with ideas how to make it, how to translate their training, their expertise, and ideas into a company. That's what we have to foster here. We have been a little bit late in the game, but that doesn't mean we can't flourish in this area. And we do have various units across the university which do that. We just have to put them together. But the most important thing is in our undergraduate and graduate student community, we have to foster a culture which really makes it cool, you know. I have no qualms at saying that, you know, you have to make these things cool to make students really gravitate towards it.
Thank you. Thank you, Sanjeev. And it is exciting to be moving the College of Science further and further towards an entrepreneurship landscape that really will make our students feel encouraged and supported as they try out entrepreneurship and realize that it is both really fun, really interesting, and can lead to things beyond their wildest dreams. Wonderful. And we're so grateful for our supporters, our donors, our families who are assisting us with moving this culture of entrepreneurship forward. Much appreciated. Sanjeev, I want to thank you, Professor Mukerjee. Thank you so much for your consideration today, for giving us really a fantastic discussion of your own research, your own directions, and the wonderful success you're having in your own group in conjunction with industry and in moving our society, our technology towards something that everyone would be very grateful to have in our pockets as responsible members of society. So thank you so much. Thank you all for joining us. It's wonderful to see this group, and we are looking forward to thinking more about this topic and working with everyone to support the college as we move closer and closer towards better and better sustainable energy. Thank you so much and have a wonderful day.
Thank you very much for inviting me. It was a pleasure. And if anybody has any questions, you can always contact me with, through email. Thank you very much.